So welcome everybody to this ISBA webinar organized by Bayesian Analysis. Today we're very fortunate to have a very interesting paper written by three authors, all of which are associated with Ohio State University. First one is John Lewis, who successfully finished his PhD at Ohio State in 2014, was supervised by the other two authors, and then went to Sandia National Laboratories and is now at a specialized loan company, I'm told, which is called Upstart. Steve MacEachern is the chair of the statistics department at Ohio State, already for second term, I think, which testifies to his selfless dedication. He has made many key contributions to Bayesian statistics, for example, in Bayesian non-parametrics, of course, but also in other areas, robust methods, computational statistics, etc. The third author is Yoon Lee, who's a professor of statistics at OSU, who also has an appointment in computer science and engineering. She focuses her research on statistical learning and multivariate analysis, in which she has produced many important publications. So as far as I know, Steve and John will present the paper, and the paper is entitled Bayesian Restricted Likelihood Methods, Conditioning on Insufficient Statistics in Bayesian Regression, and it will shortly appear as a discussion paper in Bayesian Analysis with the discussion of the three discussants that I will introduce in a moment, as well as other sort of contributed discussion. And it's a really sort of interesting paper. So even if you have, if you are in the webinar, it's still very much worth, I think, reading the paper in full detail and all the discussion. So if you have questions during the seminar, please write them in the Q&A section. So perhaps we can alert the people presenting during the presentation if there are any questions. If there are any big questions or important ones, well, all questions are important in a way, but if they would require a fairly lengthy answer, then it's probably best to wait till the end, where we might have a little bit of time for general discussion, depending on how much time people take, of course. Now, I mentioned discussants, so we have three wonderful discussants, and I was told that the order should be Bertrand Clarke from Nebraska-Lincoln, then Christian Robert, Paris-Dauphine, Warwick, and I think recently also Ca' Foscari, and then afterwards the third discussant is Fabrizio Ruggeri from IMATI in Milano. So after the discussants, the authors will present a rejoinder. As I said, if we have any time left, we'll then allow for questions, comments, and discussion from other participants. Please use the Q&A. If we have time, maybe we can allow for people to raise their hand if they want to talk and have a more sort of civilized discussion if you want, less sort of electronic one. But we'll see, depends on the time that we have in the end. So let me not take any more time and give the word to I think Steve initially, is that right?
Yes.
So if you could share your slides, Steve, then we can all see what's going on.
Here we go. I think I've got them up. Can you see them? Yes. Yay, there we go. You know, what I'd like to do is just kind of dive in, and thanks, Mark, for the very kind introduction. What I'd like to do is start by just talking a little bit about motivation for the methods. Then it'll be a little bit of a tag team. John is going to take over, talk a little bit about substantive details. And then we'll switch back to me toward the end, just to do a little bit of a wrap up before we get to the discussions that are guaranteed to be very interesting and I think lively discussions that is very, very much appreciated by us. I should mention that you know, this work, which has been going on for quite some time, supported in part by the National Science Foundation and the U.S. National Security Agency, and also the Nationwide Insurance Company, which is a big insurance company headquartered here in Columbus, Ohio. What do we have? You know, the work really began, you know, when we were trying to think about data analysis and how to really do data analysis if you're a Bayesian, which I think is of course one of the big challenges that we all face when we're trying to do a practical statistics and really use things. And of course, Bayesians have to make a few choices. And everybody in this webinar knows that Bayes is optimal, and Bayes is the best thing that you could possibly do if you make three little assumptions. And one is, that you've got the right prior distribution. We'll hear commentary on that later on, I'm sure. Second is we have choice of a loss function, that you've got a loss function so you can make your decision. And the third piece is just the sampling density that people tend to call the likelihood. And, if you have those three in place, it's just mathematics that says you have to be Bayes. It's simply Bayes' theorem. And there's no question but that is the right thing to do. Now, when we think about these three pieces, we always have to worry a little bit about misspecification. Right. And that, of course, is one of the timeless challenges that Bayesians have faced since the beginning of Bayes. We have to worry about whether we've got, the right density, the right family of models. We have to worry about whether we have a reasonable prior distribution or not, and so on. Probably the biggest concerns are the parts that do not wash out with large sample size. And so, for some of these pieces, for example, the prior distribution, if you have a wealth of data, the prior is perhaps not terribly important, right? It does play a role, but it's maybe not of central importance if you have in fact a lot of data. On the other hand, some parts simply don't wash out. And even if you get more and more and more data, they're still important. And the likelihood is probably the biggest one for general concern, because we want to get to that posterior distribution. And of course, this is what people have been wrestling with long before they were doing Bayes, when they were just trying to do statistics and look at data sets and extract information from it. In a sense, because Bayes is driven by likelihoods, the connection to data analysis is really, in a sense, about formation of the likelihood, or the primary, the primary place where data analysis bumps up against Bayes. Now, if we view things in that way, what I'd like you to do is in your own mind, think of a couple of cases or particular experimental settings that you have familiarity with. And you'll find out that there are things that are known for those experimental settings that you routinely ignore. And so, for us, we've worked a bit with people in the psychology department where they do reaction time experiments. A wonderful psych department here at Ohio State. And there are just known features of the data, right? Sometimes if people ask just to take and press a button when a signal appears on the screen ahead of them, you get a reaction which is physically too quick to be possible. And you know that they were pressing that key before the signal could pass through their eyes and get to their finger for the key press. Some are too slow, and you just know somebody was distracted, not paying much attention. Serial dependence that my colleague Mario Peruggia has documented very carefully, Peter Craigmile as well. And so what do people do? Well, a lot of times they just kind of truncate stuff, jettison some of the data. They say, well, that one is too fast, we'll get rid of it. That one's too slow, we'll get rid of that. We'll ignore the dependence. And they just clean everything up. So they have a nice, simple set of data, but then they also go with a simple model for the analysis. Right? That's the kind of thing that people tend to do in data analysis. Big corporate databases, this has to do with the insurance company that funded part of this work. They know that there are problems with their databases. Right? They have quite good data, but it's not perfect. And they have no interest in making it perfect, because the economic cost of trying to get everybody's name exactly right and everybody's address perfect would simply overwhelm them. Right? I mean, it's simply not worth it to have perfect data, but you do want very, very good data. In the US is kind of a mess for regulation. Every state has its own rules. Some are federal rules, but insurance is very heavily regulated. Rules depend by state, and that changes the competitive environment. It changes sometimes the definitions of categories or actual terms, the meaning of them, insurance. All of that kind of thing is part of the data set. And you have to wrestle with it when you're trying to build models. In a sense, there's very real model misspecification if you think about a definition of a category always having the same meaning in each and every state where the company does business. What do people do? Well, a lot of times you just kind of gloss over them and you say, well, we've done a pretty good job whipping the data into shape. And now we're just going to write down our model and we're just going to move forward. Everyone that I know when they're looking at analyses and really trying to build models, whether it's Bayes or whether it's classical, makes these kinds of choices. And it's simply the reality of practical statistics. I've got a few more listed on this slide. If you do experimental design, might be for a clinical trial, for example, and you look at it, there's going to be some kind of randomization, hopefully, maybe assigns patients to treatments. And yet, when you really look at the patients, if you can have access to the patients and see them, you notice differences, and differences that are not recorded in the covariates that you have. You talk to somebody and you have a sense, yeah, this person is really going to comply with therapy. You talk to someone else and you have a sense of, I'm not so sure that they're really going to comply. That's a difference. It's real knowledge. If you were going to be a pure Bayesian, ideally you would put that in some subjective fashion. But it's so hard to do. And so hard to do without having potentially big negative impacts on the analysis that we tend not to do it. So we do things like randomize because it's sensible, and then kind of ignore all of the details about the realization of the randomization, all the details about those experimental units. Regression, a huge class of problems, of course. We always do things to simplify our models, right? And that's often good practice. There is some work, very, very good work, Carlos Calvarjo, James Scott, and others, who say, don't do that. Model in the big space and take care of that as part of the inference problem, which is a very sensible way to deal with things as well. Non-linearities, there's always a little bit of non-linearity in regression, and we just ignore it, right? If it's modest, we tend to ignore it. If it's large, we tend to try to put it into our models. But we do all these things. We just do it routinely. It's part of I think, the practice of good data analysis. And yet it kind of clashes with Bayes. It's not the pure Bayes thing that where we would say, write down your model. Now you've got the model and just grind forward with the theorem. We're always interested in those diagnostics, juxtaposing reality against the model that we're fitting. And then we have to make decisions in the end, kind of see where we really end up. When you think about these things, again, different ones of you have different backgrounds, interest in different problems. I encourage you just to pick a problem that you really know about and ask yourself, what are you doing in data analysis where you're actually writing down and using a model where you do not have full faith or full belief in that model? High dimensional problems, I don't think any of us believe the prior distributions. Non-parametric Bayes I've worked in quite a lot. And you're writing down a prior distribution because you need to have one if you're going to do Bayes. But I don't think anybody believes the Dirichlet process captures their beliefs about the unknown distribution function. Right? We all make compromises. So what I'd like to do is sort of take the next step. And when wrestling with these issues, we decided that we'd go with a thought experiment. And this is not reality. This is just a thought experiment. Right? And so here's the thought experiment. We imagine that we have some generic Bayesian model. N cases, we believe that there are, the N cases are a random sample from some distribution, conditionally IID, fully exchangeable, and all that good stuff. And if we were to write down the full model, we'd say the density for a data vector Y given theta is just the product of all the individual likelihoods. Right? And that would be the likelihood we would use. And if you're using Bayes' theorem based on the entire sample, you would just use the product over all N cases, and that's it. But here's the twist. For the thought experiment, I'm going to tell you that there are exactly K cases that are outliers. And by outlier, I don't mean something with big residual. I mean something that is disconnected from the parameter theta. Right? There are K cases, and I'll tell you which cases they are, that have no connection to the parameter theta. Thought experiment. Right? This is not reality. Thought experiment. When you have those, everybody would say, for those K cases, there's no connection to the parameter theta. And it's ridiculous to actually just include them as part of the likelihood. And I think all of us would just cross those cases off, remove them from consideration, and say, tell us about the likelihood for the cases that are connected to theta, where we have the right model. Right? It's the thought experiment. We've got the right model. And of course, what we would do then is just go ahead and use Bayes' theorem. Right? So in this simple thought experiment, I think all Bayesians would agree that what we would want to do is just jettison the data that we know are bad data and not connect it to the parameter theta in any way, and use the data that inform us about theta. And that's really just sort of saying, well, somebody tells you you've got the wrong model and tell you how your model is wrong, use the right model. Right? Simple and clear. Here's the problem. The problem is that in reality, we don't get this information. In reality, we've probably got the wrong model connecting the theta to the y's, and we have a myriad of other problems. And so what are we going to do? Well, we're going to play off of this thought experiment. What we're going to do is we're going to use the same kind of strategy that we would for this thought experiment. But we're going to try to not just deal with outliers, deal with the real problem of model misspecification. That could be non-linearities in that regression model. It could be all sorts of deficiencies in your model. And what we want to do is we want to take and partition our likelihood into two pieces. We're going to have a summary of the data. We'll call that T of Y. It might be an estimator that gets from somewhere if the estimator has desirable properties, but it might be some other summary of the data. And what we'd like to do is really focus on the blue part, the likelihood of the summary of the data. And that's what we're going to use in Bayes' theorem. Now, that's not the full data set necessarily. And in fact, we're going to make a case that in some instances, we would prefer not to use all of the data. We prefer to restrict the likelihood to be the likelihood only for the summary statistic T of Y. But once we've made that choice, we're simply going to use Bayes' theorem based on T of Y. And of course, there are a host of issues that you have to take care of. Right? I mean, you have to be able to fit your model, which means you have to deal with computational issues. There are other issues that you've not settled in this paper that are in fact open problems. Questions about asymptotics, questions about how well this works, and many questions like that. But really what we're going to try to do is choose a good summary T of Y. Having made that choice, use Bayes' theorem and go from there. Now, I should mention, of course, there are a ton of other methods that, in a sense, restrict likelihood or very nearly restrict likelihood. Peter Hoff has written about rank likelihood. Bertrand has written quite extensively about mean likelihood and other variations on ideas that are very much like this. Christian has done very much with approximate Bayesian computation, where I think some of the same ideas pop out, and perhaps there's a bit of synergy between ABC and the techniques we're using. And there are many, many more, too many to list. But here, formally, what we're going to do is once we've chosen T of Y, we're going to be exactly Bayes. The goal is to have no approximation, although when we fit models with MCMC, there's always the MCMC approximation, which is part of it. So this is really what our paradigm is, what we're going to go after. And when we thought about this, of course, it's not enough just to say, well, we have this idea, and this is all the sorts of things you should do. We needed to instantiate it. And so to instantiate it, we said, what we want to do is think about developing these techniques for a specific setting, just so we can see how well they work and really try it out. Is there value here or not? So we did a little early work. I think the early stuff is back 2012, which is sort of low dimensional problems. But what we were shooting for is really a setting that number one is a model that people use all the time. So it's not a bizarre, weird model, which is central to Bayesian statistics. One where we know that misspecification is a very real concern and people have good sense of how the misspecification might work. Also, we wanted to compare it to classical methods to make the case that Bayes actually has value. And you can't just do this by sacrificing Bayes. And for that, we wanted to have a setting where there's a natural classical approach to the same problem. And the third is, we wanted something where we would have to develop some computation. Just so that people would see you can do this in realistic kinds of situations. And the goal is just to show that this is not just a thought experiment, and it's not just sort of a philosophy, but you can really do this in practice. And we settled on working with kind of a hierarchical Bayesian linear model, a collection of linear models that have parallel forms, one to another, all hooked together in a hierarchy. When you hook them together in a hierarchy, you have enough different parallel problems that it becomes a fairly high dimensional setting. And also a setting where Well, asymptotic normal approximations may work for some parameters. They don't just solve the whole problem. I mean, there's a real need to do the finite sample stuff that Bayes is so wonderfully good at. So having said that, I'm going to turn it over to John, and he will take and tell you all about details of some wonderfully fun stuff. John?
Sounds good. Thanks, Steve. All right, looks like I'm sharing. All right, thanks again, Steve, for that introduction. And as Steve mentioned, I'll go ahead and talk about some of the technical aspects of the paper as far as the application to a linear model. And you know, what I'll say here is, you know, the hierarchical model is a natural extension to the computational techniques I'll present here, simply by you know, you have individual linear models within each group, and this computational strategy can be taken within each group in a hierarchical setting. So the setting here, again, just right now, it's just a basic linear model. And what we're doing, based off the motivation here, we wish to condition on summary statistics, which in this form are, you know, estimators of the slope and the variance or scale parameters. So we've got estimators of the p slope parameters and then the one scale parameter. Implicitly, there are also obviously can be unspecified other higher level parameters here. But as far as the estimators go, I mean, you can think of classical M estimators, least median squares, or least trend squares. We did a lot with M estimators in the paper. So computational strategy, there were some comments on this in the discussion, and definitely point out that you can always do numerical integration as long as it's feasible. So if the parameter space is low enough dimension, that's perfectly fine. We've done a little bit with that as well. And then there's an appeal to asymptotics, which Steve also touched on. You know, these summary statistics that we condition on, that they often have a limiting distribution, which, you know, is asymptotically normal under very light conditions. And so you can use that as well to formulate your posterior, or to get an estimate of your posterior. But in situations where, you know, you have higher dimension, or you're not sure if the asymptotics have fully kicked in, you know, state of the art is to do MCMC sampling. So here, what we've considered is a data augmented approach where we're looking at the joint distribution of the parameters and y, conditional on what we want to condition on here, the summary statistic. And here, OBS or OBS is just the observed summary statistic. And when you break this down into the full conditionals, you can see immediately that the first one is just theta given y and the observed summary statistic. Well, that's just the observed summary statistic. Once you know y, doesn't really tell you anything. So this is just the full posterior. So, you know, if you have that full model where you would condition on y, you could certainly sample from this, and in most cases, or at least the cases we're interested in, right? And so you can use whatever algorithm there that works. And then really the part that takes a little bit to work out is sampling from y, conditional on theta, as well as the observed summary statistic. And so because you're sort of conditioning on the y having the same summary statistic, this is somewhat you know, takes some work to work out. And what we propose is just a Metropolis Hastings sampler where we accept or reject a full sample of y that actually satisfies the summary statistic. So y is an element of script A, or think of this as a manifold where it's just all the sets of y that actually satisfy the observed summary statistic. And we're going to do that from a well-defined distribution with support A. And just over the next couple of slides, I'll discuss how we work that out. Because of just the nature of this this space, it's actually difficult to directly sample from. But you could sample from different space or larger space and then transform it. And so the transformation here is basically the result of the properties or the common properties of these regression and scale estimates, which are laid out in the paper, but it's, regression, scale, equivariance, invariance properties that basically say if I do this H transformation with Z star, then T of Y is going to be the same T of Y obs. And so the basic idea is if we start with a Z star from some distribution and transform via H, we can just appeal to change of variables adjustments. And now you might ask, well, that might actually be difficult, and it is directly because H is not one-to-one and onto. And so thinking about how those spaces change and probability measure, it's a little bit difficult when you don't have a one-to-one onto transformation. But you can actually restrict the sample space of Z star so that from that smaller space, that transformation is one-to-one and onto. And so what we did here is just described here. So if we think about this manifold A, it's an n minus p minus 1 dimensional space with n data points. There's p regression statistics that are conditioned on, and there's one scale. So that's where you get n minus p minus 1. And then the sample space, just to kind of give you the result here, is what we sample from is the unit sphere, and this is the orthogonal complement of the column space of X. And it turns out if you do this transformation from that unit sphere to script A is one-to-one and onto. It's just algebraic proof there, and then now it's actually easier to figure out the Jacobian of that transformation by just thinking about first principles. And so I've got some pictures on the next couple slides, which of course help me, and I hope it helps others. But the basic idea is we sample from we start with a sample from a known density on the sphere, Z star, and known density. In practice we use a uniform on that sphere because it's easy and it turns out it works. We haven't noticed any serious problems with doing that yet. And then we set Y equal to H of Z star, and this is our proposal Y. And then we have to figure out what that distribution, what the implied distribution there of Y is. And so we can think about the Jacobian broken down into a couple of steps. If you look at the transformation, first there's a scaling step. So we basically move from that sphere to scale it so that the scaling statistic matches. And then, and what that does is it actually moves the initial point to this set here, which is the projection of script A onto the orthogonal complement of the column space of X. So that's just this Q here is just that projection matrix. And then the next step is taking that point and shifting it along the column space of X. And I think it'll be pretty clear in the picture that I'll show next is that this is I call it a shift, but there is a non-unit deformation or a non-unit Jacobian involved in this. And so here's the notional example that I find helpful every time I think about this problem. And when we were working out, this proved very useful. Not saying we'd ever want a condition on this statistic or ever be in a problem like this, but we have n equals 3 and p equals 1. And the statistic here is just the location or the slope statistic here is just the min of Y. And then the scale would be the square deviations from the min of Y. And just to explain, so we're all on the same page here. So if the observed summary statistic is just 0 and 1, that means the min of Y is 1, so or 0, sorry. And in this three-dimensional space, you can envision that script A to just be this light blue shape here, which is a quarter circle on each one of the planes defined by one of the y's, B and C. And then, of course, the radius here is defined by the second part of the summary statistic, so B1. And then that projection onto the orthogonal complement of the column space of X, which in this case, X is just the vector 1. And that is just this sort of warped triangle, this darker shape here. And then we're going to start on this unit sphere. In this case, it's a unit circle, but that's where we start our sampling from. And then the two steps are basically, a change of variables to this projection of A, and then another one to this original space. So kind of looking at that plane where we start, here we're just taking a sample Z star, and we can think of the change of variables to the projection of A in two steps again. So first is to just scale it here so that, this is just a change in the radius of the sphere, so that it hits a point on this space. And that's just a comparison of the volume of the sphere. And so the contribution of the Jacobian is just the radius raised to this power given the space that we're in, the dimension of the space. And then the next one is, if we look over here, now we have to sort of, the way I envision this is just kind of, melding that dash circle onto the warp sphere. And what contribution of the Jacobian there is just comparing infinitesimal volumes. You can think of this as just looking at the normals to each one of those spaces and the angle between those normals. And so the normal to the circle or the sphere is just the Z vector. That's pretty easy to work out. And then the normal, what we show in the paper, the normal to this projected space is actually the gradient of the scale statistic. And this gradient is taken with respect to the data vector Y. And so these two parts contribute to the Jacobian there. And so now we have a distribution along this projected space. And now the last part is to go back up to the unprojected space, if you will. And so this is the shifting step of Z to Y along the column space of X. And maybe just to go back here, say we ended up here. Now we just have to kind of, like I said, maybe mentioned before, just kind of warp that back onto this space. And so you can see I called it a shift, but it's pretty obvious that there will be a non-unit Jacobian transformation there. And it turns out, again, just thinking about first principles, that part is the contribution is just the ratio of infinitesimal volumes along the projection of script A at the Z point to the corresponding volume along A at Y. And we worked that out to be the volume of this P matrix, which of course can be calculated using singular values. But the P matrix here is just, again, Q is the projection onto the orthogonal complement of the column space of X, and A here the columns are an orthonormal basis for the tangent space of script A at Y. And some more details here. That space, we can actually find a basis for the complement of that space using the gradients, is what we showed in the paper. So the gradients of the statistics. And so we can start there and orthonormalize these and find the basis for the complement. And then, of course, we could, if we wanted to, then use Gram-Schmidt orthogonalization to find the basis for script A. Of course, that's actually pretty computationally intensive because this space is n minus p minus 1, so it's big O n cubed. And so that's actually prohibitive if it's set inside a MCMC algorithm. Like this is just one iteration. So in practice, actually, we just have to, we kind of demonstrate in the paper, there's a relationship between orthogonal spaces, and so we just can stay here, right, and find an orthonormal basis for this space, and then find the volume that we need from that, and describe how we did that in the paper. But it's just a linear algebra argument, it reduces the computation to a big O NP squared, so it's quite a big speed up. And so the tenor of these last slides is now we have a way to sample a Y that satisfies the summary statistics, and we know the distribution of that, and so we can calculate the Metropolis-Hastings ratio and compute the acceptance rejections and so on, acceptance and rejection probabilities, and just plug along with our MCMC algorithm, iterating between the full conditionals. And so let's get to some interesting data analysis. Once now we know how to fit these models. Steve mentioned the Nationwide Insurance Company, and so they sell many policies through insurance agencies. I believe it's just in the United States. They're pretty well known in the United States. Main headquarters is right where we are, in Columbus, Ohio. The idea is, or what happens is these agencies, you can sort of think of them as like they're individual businesses, but they have, and they provide direct service to the policyholders, but they have different contractual agreements with Nationwide. And Nationwide is, of course, interested in future performance of these agencies. And one way to measure that future performance is, or that performance is just the number of households that the agency services, right? And so this is just a exploratory view of some of the data. The labels here state, I'm referring to states in the US, and the numbers are arbitrary, 2, 15. They don't, and we've sort of sanitized this data a little bit for confidentiality. The contract types are also non-descriptive, but there are varying number of contract types, and they correspond to the various colors. On the x-axis, we have the household count on the square root scale at 2010, and then the response here is 2 years later, that same variable. And again, these numbers have been shifted and scaled to protect their actual values, but they don't actually change the relationship between any of the variables. And then, yeah, I think that's the. The other thing I guess I want to say is, I mean, when you look at this, it's clear that there's some interesting cases going on, right? There seems to be some strong linearity in parts of the data. These zero counts here are essentially agencies that were open in 2010, but they had zero household counts, whether they closed or they merged with another agency. It's sort of unknown what happened there. There, appear to be traditionally might be called outlying points, although that could be due to the variant contract types and so on. And so a pretty interesting data set because of these properties. And the first thing we did is just take at the individual state level, just fit individual regressions. The covariates here are the one I showed you on that last plot, that the square root of household count in 2010, and then 2 other measures of size and experience of the agency. So think, number of employees or years experience and so on. And the response here is the square root of household count on 2012, which showed in the last plot as well. And there's definitely model misspecification here, because we're of course we're missing covariates, but the one obvious one is contract type that's not in the covariates. And we're not accounting for closure information. So those zero counts, there's no pre-cleaning of the data or anything like that. And those are the sort of two obvious model misspecifications. Of course, there could be others that are just unknown. And this can cause many cases to appear outlined due to that misspecification.
Hey, John, just a reminder that we've got a limited amount of time to do our part. We got to get to the discussants because they're very interesting.
Okay, let me skip over the model evaluation. Let's just say that we did a model evaluation that accounted for the fact that there were quote unquote outliers in both the training and testing sets. And here are some results of the state level regression. Just real quickly, so the x-axis defines how much we had in the training set. So percent of samples used in the training set. So this was 25% and 50%, and the rest was in the holdout or evaluation set. This is our measure of the log marginal, the average, what we call trim log marginal distribution, or log marginal evaluation. And then there's just various methods, right? And so our methods here are the restricted Huber and restricted Tukey. And some things to point out is it's clear that if you just use standard normal theory regression, either classical or Bayes, you're not going to do very well. If you use classical regression, you can do pretty well. And in general, in the larger states, states 2 and say 27, there's the advantage of the Bayesian method is somewhat mitigated because of the larger sample, but there is still consistent improvement of using these restricted methods like here versus a corresponding classical method and so forth. The T model is interesting in some cases in the sense that, with less data, it seems to perform better, but once you get more data, that goes away. And I'm sort of attributing this to the fact that predicted distribution is filled up with more outlying points. So it's not a natural, method for predicting, future, so quote unquote, good data. And then the next set this is just a summary of what I just said. And then the next one is the hierarchical regression, right? And so this is a natural extension. These states are all, there's a similarity between the states and their insurance agencies, but they're all different because of their different states, different regulations, and so on. So we're just connecting them with the standard hierarchical regression setup here, where we have a slope parameter and a scale or a variance parameter within each state, and those are connected in a hierarchical fashion. And I'll mention here that here we're actually conditioning on individual summary statistics within each state. And so what I'm kind of glossed over before is that computational method can just be applied because of the conditional independence between states. It can be applied individually within each of the states. And here, this is the average across the states of the trim long marginal measure. A couple things to point out here. Again, the OLS just doesn't perform that well. The T, I'll mention here that the x-axis is a measure of how much we trimmed. That's why it's called the trimmed. And the idea here is if you don't trim enough, you might not be discounting much of the outlying points that are in the trainings or the testing set. So you need to trim a little bit more if that's the case. But again, we see some consistent improvement of our method. And then the T model seems to have the similar sort of problems. We also looked at ABC here, which looks to do very well as well. And I'll say a little bit more about that when we look at the individual results within each state that we included in the analysis. So the tenor here is that our method is outperforming ABC in 14 of the 20 states with a median difference of 0.04. And that difference in the previous plot, there wasn't any weighting by state size or anything like that. It's just raw averages of states. And if you just look at like, it turns out if that advantage that we saw in ABC pretty much goes away if you just remove this one relatively small state here. You can see there's a huge difference between the performance there. So it was really attributed to the one state there. And I think that's all I'll say there. So we can kind of get to the discussants. Yeah.
Steve, did you have any conclusion on that? Still?
I did have just a couple of slides and wrap up. I'll move through these quickly, but really just to come back to applied modeling, right? A huge question that I don't think it's enough attention. Certainly not when I took courses, and I think not enough now in most curricula. Is really when to stop modeling, right? We're taught to build models and elaborate them and make them more and more and more complex and everything, but not so much just to say, hey, at this point, if I stretch and try to model a little bit more and include something else, the overall quality of my model is going to deteriorate. And I think of that as one of the key decisions that really good applied statisticians make when I see them actually do a data analysis. A little commentary at the bottom of the slide about, sort of my take on Bayes traditions and sort of classical traditions for, robust estimation, a la Huber and Ronchetti now. What we've tried to do is really kind of blend the ideas of Bayes and also some of the ideas of classical, solid classical estimation in this restricted likelihood framework. Where again, it is likelihood focused. It is models that are driven by Bayes' theorem, but not just using Bayes on the entirety of the data, rather looking at chosen summaries first and then going with them. I saw a very good comment from Phil David in the chat, chastising me, I think, for my use of the word likelihood. And Phil, of course, is exactly right. You should consider using these methods anytime you worry about the model, and you should always worry about the model, right? For Bayes, we use the model via the likelihood, but always worry about the model. And with that, I will turn it over to the discussants.
Thank you very much, John and Steve. Bertrand, can you start your discussion, please?
Some minor technical difficulties.
Mm-hmm. You want me to change the order? I can do that if you want to.
There we go.
Excellent.
Okay, is that visible to everyone?
Yes, thank you.
Okay, then let me go to the beginning. There we go. So I have a number of comments on the paper that was just presented by the three authors, well, two of the authors, Lewis and MacEachern. And I'd like to begin by noting that the presentation was exceedingly lucid and the paper equally lucid. And I had a lot of enjoyment reading it and thinking about the ideas. And I'd like to present some of that to you. So quick review of the high points from perhaps a more philosophical level. As I see it, this paper opens our minds to new possibilities of dealing with old problems. That is to say, we're not limited to the model being the likelihood the way we perhaps were taught in as undergraduates or graduate students. And I'm going to phrase this a little bit more generally than Steve did, but I'll say it as the analyst can essentially at will identify a conditioning statistic T and a likelihood to use for analyzing a data set. And I've just copied that equation from their paper. And then you can just proceed to use a likelihood. And the authors comment on concern about outliers or more generally model misspecification. And while this seems very permissive, I'm not sure that it is particularly more subjective than other approaches, because modeling quantities are usually subjective, whether we like it or not. And this was emphasized by Steve's question, when do we stop modeling? I'm not sure we have good rules. You know, we can think about MSE, for instance, variance bias trade-off. But again, this is going to be subjective. And I rhetorically ask, how often do we seriously formulate a loss function rather than just choose one more or less for properties we want? How often do we discuss the specifics of an informative prior? Again, Steve cited the Dirichlet prior in this context. How often do we discuss the fine details of a model class? Perhaps not often enough, generally some kind of approximation. And I would submit that if we could actually address these questions in infinite precision, we'd virtually know the data generator. And I'm distinguishing here between the data generator, the entity which is giving us the data, and the model and the likelihood, and I'll come back to that. And so my point here is that modeling is typically subjective outside very well understood settings. And for the most part, we're not in those very well understood settings. Okay, so given that choosing a likelihood is already subjective, Lewis and MacEachern and Lee asked, so to speak, what's so bad about making it seem a little more subjective by introducing this extra quantity T? And there's a bit of an irony here in the sense that the authors call it a restricted likelihood, but the use is vastly extended. And so there might be some slightly better term than restricted, because it seems like such a relaxation of the usual constraints. More seriously, we can introduce bias or inefficiency from T, since T needn't be sufficient. And we inquire more generally, what is the relationship amongst these quantities, T, theta, and F? And we can, I'm sure, construct many pathological examples of T's and F's, but for common, well-behaved choices, we can expect reasonable behavior. And Lewis, MacEachern, and Lee give examples involving truncation responses and dropping factors in F that correspond to outliers. But as they admit at the end of section 1 of their paper, you could also use asymptotics to find appropriate likelihoods or restricted likelihoods. And I just wanted to cite a couple here. You can use the asymptotics for percentiles, in particular medians, if you wish. If you are addicted to MLEs, that's okay. You can feed your addiction by reading White, 1982, who gives wrong model asymptotics in the IID case. And this can be extended to the independent non-identical case. It's a little bit harder if you want to use a posterior mode, for instance, but it can be done. There's the seminal paper from Burke, 1966, which gives the support of the posterior. And this too can be extended to not identical data, and two wrong models. On the other hand, asymptotic normality, the distributional statements, don't quite extend the same way, and I'll just leave it at that. Now, I want to say the same thing in 6 different ways to make the point, and you'll see what I mean. Usually we regard likelihoods as coming from a model, but that's not necessary. And this is a point that Phil has made, I think, already today, but in previous conversations as well. And I'd like to point out that likelihoods in general are much more general than models. So we can shorthand that one by saying the set of models is a subset of the set of likelihoods. Likelihoods are a way to do inference, not necessarily to identify a model. My preferred way of saying this is in blue there. We're really doing likelihood selection for T, not model selection for Y. And I see the undergirding philosophy of their work as representing a sort of neo-likelihoodist view. You're choosing a statistic, you're choosing a likelihood for it, and then going to town, analyzing your data, coming back, of course, to do validation. And for them, the modeling is the selection of F and T rather than the model itself. Now, why might one want to do this? Well, there's generality. We can avoid detailed model and favor modeling because it's typically exceedingly difficult to do that modeling to either infinite precision or to a precision that we can persuade everybody else is 100% reasonable. There's the robustness angle. The sort of neo-likelihoodist approach should give robustness, since we are extracting key features of the data generator in the restricted likelihood, or whatever term you care to use. And of course, this leads to robustness checks for the restricted likelihood or the likelihood and for T. And most importantly, I think, the authors have put emphasis where it belongs. Validation, specifically predictive accuracy. They haven't looked at it in great detail, but efficiency and stability as well. So let me take a moment to remind you of problem classes. Bernardo and Smith defined problem classes based on where a model sat in a space relative to the true model. And he used the term M closed, M complete, and M open. And he was thinking of essentially inference problems, but his definitions can be adapted to predictors and to likelihoods, and with some hindsight, clarified to include more data types than his M open class originally did. So the M closed view is we have, in the likelihood context, a discrete set of likelihoods, and one of them is true, or at least best. Okay, so that's our classical setting. Then there's the M complete setting, to which Steve and John referred a couple of times, not by name, but implicitly. We have some likelihoods, and there may be a true or best likelihood, but it's inaccessible to us for some reason, whether it's detailed modeling of subjects in the context of a clinical trial or some other setting. And of course, then there's the M open case, where there is no true or best likelihood. We just compare potential likelihoods based on their performance relative to other possible likelihoods. So in that context, I'd like to link their work to these problem classes and observe that their approach is designed for the M complete and M open likelihood problem classes, as I've just defined them. And so the M complete case, I've used the one-way ANOVA. This is, as an example, this is similar to their clinical trials example, but our analyses are based on basically X bar and S squared. Now, the real strength of their methodology, as I see it, is that they're extending likelihood methods to M open problems where we don't have enough methods. And quoting from a discussion Steve and I had quite a while back, their approach looks like it can be extended, or at least used, with automated collection of large observational data sets. And I don't know if the insurance company data set they used falls into that class, but quite possibly it does. And again, this is possible because their neo-likelihoodist view rests on validation. We're not actually thinking that we believe in a model. So let me wrap up. Where is that now? Something is wrong here. My screen just froze. I don't know if people can still hear me.
I can see the last slide.
Okay, good. Okay. No, I did something bad. Let's try again. Yes. Yes, so I strongly support their neo-likelihoodist plus validation program. And I want to say just a little bit more about the validation. Emphasizing validation has a long history. I'll just mention a few. David, 1984, plus various of his other major works. The frequential principle is, in a sense, a key validation concept. Shao observed that you should use more data for testing than training in cross-validation. And that too is essentially a validation concern. From the robustness standpoint, which is also can be regarded as a sort of validation, there are techniques from Wu, Booz, and Stefanski, where you add normal noise to your data and see how that affects downstream inference. So there's a lot more there to discuss, but I'll conclude with the observation that one of the extra strengths that may not have been explored of their proposal is that it enables Bayesian exploratory data analysis simply because we can, at least in principle, invoke a statistic, a simplified likelihood, restricted likelihood if you wish, and get information of all sorts out of the data based on our various choices. And so I'll close by thanking the authors again for a lovely presentation and an excellent paper that I shall reread.
Thank you very much, Bertrand. Christian, do you have your slide or slides ready?
Yeah, let's try to.
I think Bertrand may have to unshare his screen first.
Oh, okay.
That's done. Good.
Okay.
Yep. Great.
Okay, so first, let me state that, I mean, I found this paper quite exciting when I read it. And actually, I read two papers, or the way I read it was to see two papers in the paper. In the sense that the authors were or are addressing this notion of conditioning on an insufficient statistic, which is a terrific problem in itself, and then for inference reason, and then the simulation parts, which for me is quite an interesting area as well. And so maybe because I was reading two papers and one, I got a bit disappointed by not seeing the entirety of two papers. Anyway, let me go back to the beginning. Namely that indeed the likelihood, as pointed by both the authors and Bertrand, is something that you cannot always trust. And from a Bayesian point of view, there should be versions or alternatives to, to overcome this lack of trust in the likelihood. And so here are a few that to me are of interest. And started with models that are sub-defined, not entirely defined, but set by moment conditions, as you often find in some econometric literature. And this connects with redefining the model through empirical versions, like, for instance, the empirical likelihood Bayesian approach, the replacement of the likelihood by loss functions in an approximate Bayesian version, following, for instance, the development of Bissiri, Holmes, and Walker, which I find quite fascinating, and it's still going on today as a robust approach to Bayesian statistics. Again, when you really don't trust the likelihood. And then, obviously, from my own interest, I connected entirely with the ABC approach as a form of robustification, which in its most rudimentary presentation is replacing the data with a ball around the observed summary statistics. So, the statistics that is almost never sufficient. And then I can see also a connection with an approach that I discovered at MCMSK in Chamonix, namely the existence of cut models, and that we explored in a more recent paper by Pierre Jacob and courses, where part of the models are not trustworthy, and therefore only a part of the observations are used to infer about a subset of the parameter. And then another direction that we also explored, and many others explored, is to include non-parametric components into the original model to allow for misspecification beyond outliers. And still within the ABC connection, I want to point out that actually ABC has been studied for its robustification properties in the sense that, contrary to my initial intuition, ABC can be quite resistant to misspecification, despite using a generative model. Okay, I think that for interest of time, I will not proceed through the description of Bayesian empirical likelihood. It is simply replacing the observed, a fixed or completely constructed likelihood by a construct that is only exploiting some fixed moment equation and the data, of course. But inference is feasible using that substitute with potentially interesting results. Now, the second one I want to make maybe more closely to the paper is that outliers are only one type of misspecification, and there is a much broader and, of course, infinite universe in the misspecified world. They are nicer than the average misspecified model in that they allow for mixture representation, which itself allows for replacing the original model with a mixture and maybe a non-parametric component. They still assume that the original model is relevant for some observations within the sample. And therefore, this notion that there is good data versus bad data is making a sort of a strong assumption to start with. Now, another approach that is always thought as an opposite to mixtures is in a sort of geometric mixture, which reminded me a little bit of Peter Grunwald safe Bayes approach, which is a way to back away from the likelihood to reduce the input of the data without putting too much assumptions on which part is important and which part is not. And so, I mean, outliers are only one type of misspecified burden, because there is no limit to how misspecified a model can be. Now, the approach of fielding an insufficient statistic, again, is pretty central to most of ABC, even though we and others try to work for ABC solutions without going through the pinhole of using statistics. It's most of the time using a summary statistic is a way to reduce the dimension close to the dimension of the parameter, and to allow for small, in a relative sense, values of the tolerance. But outside this ABC context, I think the difficulty with the proposed approach is that it relies immensely on the choice of the statistic T, and therefore it just moves the difficulty with modeling into another part of the space, but part that is still present. How relevant this statistic is, and how can we assess that we made the right choice of the summary statistic? So, I mean, I always feel wary when hearing the word robustness, because it feels like a very subjective concept that is rarely properly defined or reassessed. In the aspect of sufficiency, I mean, I completely understand the point that if you use an insufficient statistic, you are changing the posterior and therefore restricting the inference or reducing the information. However, if you're considering misspecification, there is hardly any meaning for sufficiency, because if the model is not correct, maybe the order statistic is sufficient, and even then it's not clear. Note that sufficiency is also a possible hindrance in ABC setups, especially for model choice, because well, if you focus on sufficient statistics for the different models, it may be that the corresponding model choice is totally inconsistent. More on ABC, namely that in the experiment there were some comparison between MCMC and ABC. In a sense, it's not so relevant in my opinion, because whenever you can run MCMC, ABC is as a disadvantage, given that it takes roughly the same time or worse, but piles up the hindrance of being approximative. Yeah, there was this sentence of that this method was ABC with epsilon equals 0. I'm not totally understanding this point, but that's not so important. I just want to notice that within the ABC convergence literature, epsilon equals 0 is not the right choice to make. It should be related to the sample size and to the speed of convergence of the statistic to its asymptotic mean. And the two next points are not of stronger relevance. It's just that ABC gives work out in any setup, but has to be itself validated, because it's not using a coherent distribution across the parameters. So it's defining a Markov chain with possibly no stationary distribution. And then we come to the part of the paper that first attracted me the most, that essentially for the wrong reasons, namely the possibility of running MCMC on manifolds. So, I mean, there is a large component of the paper that validates completely rigorously the simulation technique of producing Y's conditional on the realized value of the statistic T. And it's a kind of a paradox because given that the proposal is to seek the posterior given T, the simulation of Y given T, especially because T is fixed at the observed value, is not directly relevant. So it's purely a simulation gimmick. I mean, a trick to construct a Markov chain on theta given T. So the Y becomes ancillary in the simulation sense. I mean, the Y you simulate will be there to simulate more easily theta given T and 1 for that thing. So but when looking at the proposal, it's focusing on the linear model given a location scale summary statistic that is fixed. And so it's a very peculiar case that I find difficult to see expanded to a more general case. And if I take the parallel with the ABC setup, if you think of the original problem of inferring the parameters in a population genetic model, in the number of summary statistics, maybe over 100, how could I simulate my original data given 140 summary statistics? That's very unclear how this principle can be extended.
Christian, sorry, we're running a bit short of time, so
yeah.
you could
so this is the last
slide. Maybe.
Okay, this is the last slide. I was wondering if I mean, to conclude, the assessment could be done by using different resolutions to compare the outcome rather than focusing on a very finely tuned algorithm. And there are proposals in the literature that I listed here that tries to go further than this location scale structure. So again, congratulations to the authors. It's a very challenging paper and quite interesting in the area of Bayesian misspecification, which is unexplored in my opinion.
Thank you very much, Christian. So if you could unshare your slides, then Fabrizio can perhaps share his.
Yes.
I did something different from what I did before, so I have to do it again. I try to do something smarter, but it's better if I do the screen, full screen. Okay. This is
Can you make it a bit bigger, Fabrizio? There we go. Fantastic.
Yeah. Okay.
First
of all, thanks a lot for inviting me to discuss this nice paper. And let me start with a mistake in the rejoinder. The authors misspelled my last name, so that's really the biggest mistake they made in their paper.
Unforgivable.
Unforgivable, by the way. So my discussion will be quite short. I would like to start with a curiosity about foundations. Then I will give a brief showcase of alternative approaches, some comments and concerns about the approach, but making no questions, no comments about the computational part. The previous discussant did this job. So my question about foundation is the following. So we've been taught to believe and to trust in the likelihood principle. How do you behave in this case? What is your reaction to the likelihood principle in this case, especially when there are two different conditioning statistics? Should we get two different restricted likelihood? So we should get two different information on data using the same data, and that somehow is against the likelihood principle. And then just some of other approaches. Well, one, by dealing with this kind of problems, one could try to use some distribution which is even more robust than the usually robust distribution. For example, this one due to Box and Chow, I copied what Shamal Kumar wrote in a book I edited with Adirios. This distribution here, which has as a particular case the normal, the Laplace, it's like also the uniform. It has a lot of very nice properties. So this kind of distribution could be useful to try to deal with these outliers in some way. Then there is what was one of my favorite topics, is Bayesian robustness. And in the case of sampling models or livelihood, we have to deal with outliers, in this case, with a class of statistical models or neighborhood of livelihoods, and then the computation of the range, lower and upper bounds on the Bayesian estimator of the parameter of interest. This was the typical approach of Bayesian robustness. There are some results in these directions. I shall mention a couple. One, a very important one by Michael Lavini in his JASA paper in 1991. I'm just quoting the abstract. He says that the paper introduces the method for computing ranges of posterior expectations over reasonable classes of sampling distribution that lie close to a given parametric family. It's a very nice paper, and I suggest to have a look at this one. Shamal Kumar considers something more traditional in Bayesian robustness, so classes of sampling distribution like the one in which we have zero, it's an epsilon contamination of that one, so 0.9 a Gaussian with parameter theta, plus 0.1 a Q, which is a symmetric unimodal around theta. So these are kind of approaches. Also, there are others in my unpublished work. I consider infinitesimal perturbation of the likelihood of the Fréchet derivative. But I just want to mention a very recent work with Chaitanya Yoshi that you just submitted. And here we start from the case in which we have the usual Bayesian analysis with our data, with X naught, a prior, and we do the analysis. But then we can assess sensitivity to uncertainty in the data, which is something similar to what Steve and John have done and the other co-authors have done in their work, at least in terms of ideas. So we could have observed different data in this case. So what we do is try to consider a class of priors. So move from this uncertainty in the data to a class of priors to do after having performed the usual Bayesian analysis. And so we are going to consider some data, hypothetical data, which could be closer to the observed one. We take the likelihood ratio between these two densities in this case, and then we build a class of priors, which is proportional to the initial prior times the likelihood ratio. So you can see there are a lot of other alternatives to the one that you have been proposing. But then coming to your work, here I'm just quoting again what you wrote about the choice of the tuning parameters for the M estimators. You wrote, the tuning parameters associated with these functions are chosen so that the estimators are 95% efficient under normally distributed data. I'm wondering, is this a Bayesian sentence? Is this a Bayesian approach? Or should we use other ways, for example, based on loss function, which should be sounder from a point of view of Bayesian statistics? From a point of view of practical use of what you did, I'm wondering if there is any guidance on which M estimators are recommended in different situations. And also, if you have to choose different M estimators and also different parameters in these M estimators, is there a sort of approach like a Akaike, AEC-like approach to choose among them, or like the other approaches that we usually use? And my very last slide is about possible extensions of your work. For example, in stochastic processes. And I was thinking about a Poisson process, a non-homogeneous Poisson process with intensity function lambda t of theta. And we have used that to model bugs detection during software testing in a time interval 0t. Let's suppose that n bugs have been detected at time t1, t2, tn, which could be less or equal than capital T. Then the likelihood is just the product of the intensity function at the points in which we detected the bugs, e to the minus the mean value function, which is the integral between 0 and t, so over all the intervals of the intensity function. Okay, suppose that in this case we have larger times between two detections. That means the software is very reliable because there are not many bugs to be detected. But at some point, there is a very small inter-arrival time. For example, T3 minus T2 is very small. So we could think this is a sort of outlier in this case, because that might correspond to a very bad, very unreliable software, and that would be removed. And this is a debatable decision. In general, I have some concerns about removing data when we are observing them. At this point, I'm asking, how do you get restricted likelihood in this case? Look at the form of the likelihood. Well, we could remove the lambda related to T3. That's okay. But what about this term? What should we do? Should we remove the integral between T2 and T3, leaving as it is not easy. And also, which kind of sufficient statistics, M estimator, should we use here? So if you want to have your approach applied more successful, you should think also of other applications rather than the one you have just presented. In any case, thanks a lot for your talk. And now, interrupt. Thanks.
Thank you very much, Fabrizio. So, Stephen, John, do you have a little bit of time for the rejoinder? If you have slides for that, or just want to do it without slides?
You know, I actually do have I do have a few slides. If I can pop them up,
Sure.
We'll see if I can pop them up. And yet I'll try to be quick, respecting the time constraints. So just just kind of a little bit of a recap and overview of the discussants. They kindly sent slides ahead. You know, stepping back, right? Old times, 1990s, for example. You know, Bayes versus classical stuff. Bayes won so clearly and so completely that classical statistics was forced to change. And, you know, if you look at it, you know, the big question was, how could you use Bayes to really do applied work? And MCMC just opened all that up, right? And it was so easy to use that problem after problem, Bayes was just better answer every single one. And I think there were two drivers for that. One is that, you know, mathematics is actually true when done right. And all those beautiful theorems about decision theory that talk about admissibility are actually theorems. And they are right, and they're true, and they're real. And the models that we write down are often close enough matched to reality that you see the improvement. So if you want to predict well under squared error loss, you know, use an admissible rule, and all the usual stuff applies. Second is that we can, with Bayes, very easily incorporate information, not just the small experiment, but other information that we have about a problem. And those two drivers, it was just every single problem. Bayes was the winner. Classical people didn't like it, right? And you guys probably have good friends who are classical people. I know I do. And so they fought back, right? And what could they fight back on? Well, they could say MCMC is slow and it's faster now than it used to be, but, you know, it's still kind of slow. And so they, you know, speed, penalized likelihood, but then there's variational Bayes, right? Which is a different kind of approximation, but also very, very fast often. Huge data sets, MCMC would often start to break down, and some of the penalized likelihood methods would not. We see a lot of poor quality data now, automated data capture, enormous data sets, and we can't really say find all the outliers and influential cases and do all that. We have to deal with things in the aggregate, accepting the fact that some of the data in our data set is simply of low quality. And of course, it's not only if you split into test and training and validation sets, it's not only in the training set, right? I mean, it's in the validation set as well. Third thing, of course, complexity of data sets. A lot of times now we see not only more covariates, more dependence structures just present in the data sets, but we combine different collected data sets, all of which are a little bit different in reality, sort of the terms, definitions, and we have to stitch them together. Modern times, new challenges, and these are new challenges for Bayes. We can respond to all of these challenges, and people are working hard at doing it right now. And this generates some of the big, exciting problems for Bayesians now. So that sets the stage. Big themes from the discussants, and this is loosely right. I mean, I love the actual discussion and the explanation of things today. I think all of us agree on the importance of doing serious data analysis. And it just carried through from all three discussants. We really have to look at these techniques. We have to think hard about how we're building models, about how we're implementing Bayesian methods. The truth is we're not really in the M-close situation, although that's kind of what we're all trained on in those first courses where we see Bayes' theorem. Christian in particular, but also Bertrand and Fabrizio, all three, lots of different alternative approaches to robustify Bayes. I mean, there are many, many different approaches, and we heard about a few of them. It is absolutely right. When I think about it, we have our proposal we talk about in this paper. We think it's worth pursuing. It's a good line going forward. But it's very true that many of those other lines are really valuable lines going forward. And the question is not, is one of them right? And should everybody pursue a single line right now? They all should be pursued and pursued hard by the Bayes community. And the question is, where are we going to be in 10 years? Where, we'll find out that some things work super well, some things kind of don't really work, others kind of work in certain situations, but not others. As a community, we need to pursue all these lines because all of them are going to add value. And the truth is not going to be any individual one of them, I don't think. I think it'll be taking elements from these different approaches and creating something new, which is the future. It's not yet here. A little bit, Christian perhaps most particularly, but Fabrizio as well with his last example. Unusual data points are not necessarily bad. Things that look like outliers can very much be part of the data. It can be very informative for the scientific problem at hand. Absolutely. It's not to say that they're always good data, right? I mean, sometimes it really is bad data. Our take on our work is that it's not really about outliers, but it's about model misspecification. We hope to do a bit more in further work that looks at cases where it's just clearly not outliers at all, but rather other kinds of misspecification that are driving things. And different problems will require different summary statistics. They require different choices and different implementations, and that is part of the future. Last little bit, there wasn't a lot on this. Asymptotic approximations are, of course, great. If appropriate, they are quick, they're accurate, and they do wonderfully well. They're not always appropriate, which is why MCMC had such an impact on Bayes, but also on the world of statistics. One extra bit, it's nowhere in the paper, but it's tied to our thinking on this. And it just goes back, when you think about these things, they always have an impact on big problems in statistics. One of the early things for classical statisticians is just in fact, wars between Fisher and between the Neyman Pearson school. How do you do hypothesis testing or significance testing? What's the right language? Can you accept the null? Do you only fail to reject the null? All those great things. And that's very real stuff, right? Neyman and Pearson, this is a bit of a character, an exaggeration, right? Caricature. Pretty much they say a likelihood ratio, right? And if you have nuisance parameters, just take a soup over the nuisance parameters, generalized likelihood ratio tests and all that. Tests work really well. Fisher, he was a choose your test statistic guy, right? And after you chose a really good and meaningful test statistic, use that and see whether the null stands the test of the statistic or not. Now, many of his tests were likelihood ratio tests, right? But he was choose a good statistic. Bayes, of course, driven by likelihood after you've written down your model, but integration instead of the souping that you see in Neyman Pearson. Here, we're kind of doing something that maybe brings Fisher and Neyman Pearson a little bit closer together. Choose a statistic, very much what Fisher would do. But once you've chosen the statistic, not just sort of tell me about a tail area, but rather use that statistic and focus on the likelihood. Our tilt, though, of course, is to move toward Bayes, to actually do the integration rather than souping over nuisance parameters. And, so I think there's something here about testing. A full suite of inferences follows from this, right? You can do model selection and things. You have to be a little bit careful about choice of the summary statistics, but you can do a lot of this. And, you can do Bayes factors if you want, but you can also do, what I would think of as more real Bayes that includes prior probabilities for different statements. Prediction works well for these methods as well. It just sort of pops out if you have a posterior and you have some kind of formal model written down. Of course, you can make predictions, which is a nice feature. And then just the last bit, thanks to everyone. The editors who not only asked us to do the webinar, but really nice work, nice thought on Michele's part to actually create the webinar series. They're wonderful things for the community. Discussants, really fun. I'd love to sit down and talk to people in person sometime more when we can actually meet and talk in person. Apologies to Fabrizio about butchering his name. There are other written discussions in Bayesian analysis and some really, really nice discussions that people have written that touch on some of the questions raised by the different analysts. Read those discussions. There's a lot of wisdom in those discussions as well. And the big thing is, man, hopefully we'll all be together in Montreal for the big World ISBA meeting. Travel restrictions hopefully disappear by then, and hope to see you all there. That's it for me. So thanks very much for your attention.
Thank you very much, Steve. I know it's woefully late and we've overstepped the mark very much, but I think it's such an interesting discussion. I still would like to give the rest of the audience perhaps a little bit of an opportunity for a few minutes to comment. And somebody who's been putting his hand up a couple of times during the talks has been Phil David. And I think if I can still find him on the list, I'd like to give Phil maybe the opportunity to say what he had in mind, if he's still here, unless he's just gone very quickly. Let me just check. Okay, no, I can't see him anymore, I'm afraid. Okay, so Phil's gone. Anybody else wants to raise his hand, her hand, their hand, and maybe provide us with a comment or suggestions or questions? Or I know there's one question which I don't know what has been answered or not, a question by Chin Shapland on can you explain why the ABC model performs better? Not very clear. I think, John, were you typing an answer to that?
Yeah, I actually didn't want to get distracted by the discussion. Let's see. I think maybe there's two parts, I guess, to this answer. One is that it seemed that the improvement was only in one state. So if you kind of remove that one state, it goes away for the ABC. And then the second part is quite honestly, and I sort of hate for this to be the answer, but after that, we didn't really dig much deeper into that question. And so there's where we stand on that.
Okay. All right, thank you. Any further comments, questions, suggestions? No? Okay. Well, then, thank you very much. Thanks very much to everybody who's still online for your patience, because it's entirely my fault that we ran over quite a bit on the sort of suggested schedule. But I didn't want to cut it short because it was indeed a very interesting discussion. So thank you very much to all of you. And indeed, as Steve was saying already, I very much second that. I very much look forward to seeing all of you in person again at some venue, possibly Montreal, possibly something else in the not too distant future. So hopefully we'll get back to a little bit of normality again. We can have these discussions in private, in person. I mean, with a lot of added sort of excitement, I imagine. So good. Thank you very much.